And now in this lecture I will answer two questions. In the first question we find out they have this green shape, and in the second question we will find out the length of this line segment PQ. We find out the length of this line segment PQ that is equal to x. We have to find out the value of x. So we start with the first question. In the drawing we have a circle inside this big semicircle. We know that this is line segment AQ, that is equal to 4 units in itself. This is angle PQA, that is a right angle. This is line segment TB, that is equal to 1 unit in itself. This is angle STB, that is a right angle. Again, our task is to find out the area of this green shape. So first of all, we will define the radius of this big semicircle as x and the radius of this small circle as y. So I write it down. X is the radius of the big semicircle. And y is the radius of the small circle. In the next step, we will define the center of this small circle. This point is point O, and we will define the center of this big semicircle. This point is point C. We define the point of tendency of tangent AB with this small circle. This point is point N. Likewise, we define the point of tendency of tangent PQ with this small circle. This point is point H. We define the point of tendency of tangent ST with this small circle. This point is point L. And finally, we define the touching point of this small circle with this big semicircle. This point is point K. In the next step, we will join points O and N together by a straight line. Point O is the center of this small circle, point N is the point of the small circle itself, therefore ON is the radius of this small circle. This is equal to 1 unit in itself, according to our definition. The radius ON, that is equal to y, the radius ON is drawn to point N, that is the point of tendency of tangent AB with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. If AB is perpendicular to NO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. It is given us the question that this is angle PQA, that is a right angle. AB is the diameter of this semicircle, so AB as a diameter, it is absolutely a straight line. So if you focus on the upper side of this straight line AB at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line AB at point Q? We have this angle that is right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. Likewise, it is given us a question that this is angle STB, that is right angle. So if we focus on the upper side of the straight line AB at point T, here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the upper side of the straight line AB at point T? We have this angle that is the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we join points O and S together by straight line. OS is of course the radius of this small circle. That is equals to Y. The radius, actually OL. OL is the radius of this small circle. That is equals to Y according to our definition. The radius OL that is equals to Y. The radius OL is known to point L. That is the point of tendency of tangent ST with this small circle. And whenever you have radius that is known to the point of tendency, then tangent ST will be perpendicular to the radius LO. If ST is perpendicular to LO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1, of course. So in quadrilateral OLTN, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees, and therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral OSTN we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must meet this rectangle if not a square. So we relate to quadrilateral OSTN as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So a rectangle OSTN, side OS must be equal to the opposite side TN, but OS is Y, therefore the opposite side TN must be also equal to Y units in its length. We repeat on the same process on this side of the drawing. That is to say, we join points O and H together by straight line. OH is of course the radius of this small circle that is equal to Y. The radius of OH is known to point H, that is the point of tendency of tangent PQ with this small circle. And whenever you have radius that is known to the point of tendency, then tangent PQ will be perpendicular to the radius HO. If PQ is perpendicular to HO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. So inside the quadrilateral HO and Q, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total it must be equal to 360 degrees according to the rule. Then the sum of the angles in any quadrilateral is equal to 360 degrees, and therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral HO and Q we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be this rectangle if not a square. So we relate to quadrilateral HO and Q as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So an rectangle HO and Q, side HO must be equal to the opposite side NQ. But HO is Y, therefore the opposite side NQ must be also equal to Y units in its length. This is line segment QT. Line segment QT is part of the straight line AB. Again, line segment QT is part of the straight line AB. And therefore QT must be also a straight line. Because a part of a straight line must be also a straight line. A part of a straight line is a straight line, therefore QT is also a straight line. So in total, Qt must be equal to Qn plus Nt. So Qt equals to Qn, that is y, plus Nt, that is y. Y plus y is 2y. So Qt equals to 2y units in its length. AB is the diameter of the semicircle. The radius of the semicircle equals to x, therefore the diameter must be equal to 2x. So now, AB, the diameter AB equals to 2x. It is twice as long as the radius, that is x. From one side, but from the other side, AB in total must be equal to AQ plus QT plus TB. And again, if you found out that AB in total must be equal to AQ plus QT plus TB. AB is equal to 2x, must be equal to AQ. AQ is 4 plus QT. QT is 2y, according to what we already found out, plus TB. TB equals to 1 unit in its length, according to what is given as the question. So in total, we found out that AB is equal to 2x equals to 4 plus 2y plus 1. So 2x equals to 2y. 4 plus 1 is 5. So in total, if we found out that 2x equals to 2y plus 5. Here we will subtract 2y from this equation and finally get that 2x minus 2y equals to 5. Here we take 2 as a common factor from those two expressions. So inside the brackets we have x minus y equals to 5. Here we will divide this equation by 2 and finally get that x minus y equals to 5 over 2. 5 over 2 is 2.5. So if you found out in total that x minus y equals to 2.5. What is the length of this short line segment Cn? From the drawing it is very easy to see that Cn in total equals to Cb minus Nt minus Tb. Again, Cn in total equals to Cb minus Nt minus Tb. So I write it down. Cn in total equals to Cb minus Nt minus Tb. Read again. Cn in total equals to Cb minus Nt minus Tb. So Cn in total equals to Cb. Cb is the radius of this semicircle. Is equals to x units in its length according to our definition. Minus Nt. Nt is y. It is the radius of the small circle. Minus Tb. Tb equals to y units in its length according to what is given as the question. So in total we actually found out that Cn equals to x minus y minus 1. We already found out that x minus y equals to 2.5, so we can substitute x minus y here by 2.5. When we do it now, we get that Cn in total equals to x minus y is 2.5 minus 1. 2.5 minus 1 is 1.5. So in total, we actually found out that the length of the missing line segment 97 cm is equal to 1.5 units in its length. So actually, this is the short 97 cm is equal to 1.5 units in its length. So I did know in the drawing that cm equals to 1.5 units in its length. In the drawing, the small circle touches the big semicircle at this point K. So we have an internal notch between the big semicircle and the small circle at point K. Whenever we have an internal notch between two circles or semicircles, we can implement all 9. So I take circle of all 9, and after it, I will implement all 9. We'll implement all 9 in our drawing. According to all 9, if two circles touch each other internally, then the straight line that connects the circles together passes through their touching point. Okay, again, if two circles touch each other internally, then the straight line that connects the circles together passes through their touching point. So in the drawing, we have two circles. The center of the big circle is 0.0. The center of this whole circle is 0.m. The straight line that connects the circles together is of course the straight line OM. And according to this whole line, the straight line OM must pass through their touching point, that is point P. Again, according to all 9, the straight line OM must pass for point P, that is their touching point, the OMP, or OMP is one straight line. Again, OMP is one straight line. So we can implement all 9 in our drawing. Well, because in our drawing, we have an internal notch between small circle and the big semicircle at this point K. Therefore, we can implement here all 9. According to all 9, the center of the big semicircle is at point C. The center of this small circle is at point O. The straight line that connects the centers together is of course the straight line CO. And according to all 9, the straight line CO must pass through their touching point at this point K. Again, the straight line CO must pass through point K, that is their touching point. COK is one straight line. So we join point C and O together by a straight line. So it is very easy to see in the drawing that the straight line CO indeed passes for point K, that is their touching point, or COK is one straight line. Again, COK is one straight line according to all 9. If COK is one straight line, it means that CO must be equal to CK minus OK. Again, CO must be equal to CK minus OK. So I write it down. CO in total must be equal to CK minus OK. So CO in total must be equal to, this is 97 CO, that must be equal to CK. CK is the radius of the semicircle, is equal to X minus OK. OK is the radius of the small circle, that is equal to Y. So in total, we actually found out that the missing 97 CO equals to X minus Y. This is the missing 97 CO, that equals to X minus Y units in its length. But we have already found out that X minus Y equals to 2.5. Therefore, the length of the missing 97 CO is equal to X minus Y, it is equal to actually to 2.5. We have already found out that Cn equals to 1.5 and On is the radius of the small circle that equals to y. So in the next step I'll copy the right triangle O and C in the new equation. We will implement the Pythagoras theorem on this right triangle, triangle O and C. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Repeat again, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Cn equals to 1.5 units in its length. We just right now found out that CO equals to 2.5 units in its length. Inside On is the radius of the small circle that is equals to y. So here by Pt is the evaluation for Pythagoras theorem. So actually this is the right triangle OCN that according to the original drawing. This is right triangle OCN. OC squared, that is the square of the hypotenuse, must be equal to ON squared plus NC squared. So I write it down. OC squared, that is the square of the hypotenuse, equals to ON squared plus CN squared. The hypotenuse OC equals to 2.5 units in its length, therefore OC squared is 2.5 squared, that is 6.25. And it is equals to On squared. On is y, therefore On squared is y squared, plus Cn squared. Cn is 1.5, therefore Cn squared is 1.5 squared, that is 2.25. So in total we should found out that 6.25 equals to y squared plus 2.25. So here we will subtract 2.25 from this equation, and we will get that 6.25 minus 2.25 is 4, so 4 equals to y squared. Here we take a root out of this equation, and finally we get that y equals to the square root of 4, that is 2. So we found out that the radius y of the small circle is equal to 2 units. We have already found out that x minus y equals to 2.5. X minus y. So y is 2, so this is y by 2. So x minus y is x minus 2. This equals to 2.5. Here we will add 2 to this equation, and finally get that x, the radius of the semicircle x, equals to 2 plus 2.5 is 4.5. X equals to 4.5 units in its length. 4.5 is 9 over 2. Our test is to find out there of this there of this green shape. So what is there of the green shape? from the drawing, it is very easy to see that the area of the green shape equals to the area of the big semicircle minus the area of the small circle. So write it down, the area of the green shape in total must be equal to the area of the big semicircle minus the area of the small circle. The area of the semicircle, the radius of the semicircle is x. Therefore, the area of the semicircle must be equal to pi x squared over 2. This is the area of the circle over 2. That is to say it is pi x squared over 2. Minus the area of the circle. The radius of the circle is y, that is 2. Therefore, the area of the circle must be equal to pi y squared. So pi x over 2 is pi over 2. X is 9 over 2, therefore x squared is 9 over 2 squared minus pi y squared. Y is 2, therefore y squared is 2 squared, that is 4, so in total this expression equals to 4y. So if you found out that the area of the green shape in total equals to pi over 2 times 9 over 2 squared minus 4 pi. So the area of the green shape in total equals to pi over 2, we'll open the brackets here, 9 over 2 squared is 9 squared, that is 81, over 2 squared, that is 4. So total, the value of this expression is 81 pi over 2 times 4. 81 pi over 2 times 4. 2 times 4 is 8, minus 4 pi, that is the area of the small circle. Here we will multiply minus 4 pi by 8 and then we'll divide it by 8 in order to become comfortable with this expression, and we get that 81 pi over 8, and we have minus 4 pi times 8 is minus 32 pi divided by 8. 81 pi minus 32 pi is 49 pi over 8. 49 pi over 8 is 19.24 square units. So actually found out that the area that we are looking for in this question, that is the area of this green shape, it is equals to either 49 pi over 8 square units in its size, or in terms of numbers, the area of this green shape is equal to 19.24 square units in its size. So we finish with the first question. In the next step, I will present you the second question, and we will solve the second question of this lecture. Our task in the second question is to find out the length of this line segment PQ is equal to x. We have to find out the value of x. So in the drawing we have a semicircle. Point O is the center of this semicircle. This is line segment QS, that is equal to 2 units in its length. This is line segment SB, that is equal to 1 unit in its length. This is angle PQS, that is a right angle. This is angle PTS, that is also a right angle. Again, our task is to find out the length of this line segment PQ that is equal to x. We have to find out the value of x. So first of all, we will complete the semicircle to a circle. We complete the semicircle to a circle. So we completed the semicircle to a circle, and we will extend line segment TS by straight line until it touches the circle. And we will define the touching point of the extended line segment TS with this circle. This point is point M. In the next step, we will join points P and N together by straight line. Again, we will join points P and M together by straight line. By doing all those constructions, we get the peripheral angle PTM. This is peripheral angle PTM. This is equals to 90 degrees in its size according to what is given in the question. And peripheral angle PTM subtend on chord PM. Again, peripheral angle PTM subtend on chord PM. So here we can implement rule 5. Repeat quickly rule 5. According to rule 5, any peripheral angle that is equal to 90 degrees must subtend on the diameter of the circle. In the drawing we have a circle. This is peripheral angle MAN that is equal to 90 degrees in its size, and therefore according to this rule 5, peripheral angle MAN must subtend on the diameter of the circle. And indeed, peripheral angle MAN subtend on the diameter of the circle because MN is the diameter of the circle. So, according to this rule 5, any peripheral angle that is equal to 90 degrees in its size must subtend on the diameter of the circle. So, we can implement rule 5 in our drawing. In our drawing, we have peripheral angle PTM that is equal to 90 degrees in its size, and therefore according to rule 5, peripheral angle PTM must subtend on the diameter of the circle. Peripheral angle PTM subtend on chord PM, and therefore according to rule 5, PM must be the diameter of the circle. So write it down. Chord PM is the diameter of the circle according to rule 5. It is given us the question that point O is the center of the circle. Point B is the point of the circle itself, therefore OB is the radius of this circle. the radius OB equals to OS plus SB. Again, OB equals to OS plus SB. And again, OB equals to OS plus SB. So OB in total equals to OS, that is 2, plus SB, that is 1. So OB in total equals to 2 plus 1, that is 3. So if you found out that the radius of this circle equals to 3 units in its length. So the radius PO must be equal to 3 units in its length. And the radius SOM must be also equal to 3 units in its length. In the next step, we will do a construction. That is to say, from this point S, we will do a perpendicular on the diameter PM. Again, from point S, we will do a perpendicular on the diameter PM. So actually, this angle equals to 90 degrees. And this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point S and the diameter PM. This point is point N. By doing this construction, we can do the small right angle, triangle S and O. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other. So in the right triangle PQO, this angle equals to alpha. This angle equals to 90 degrees, and therefore this fat missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in a triangle. Likewise, in this small lower triangle OSN, small lower right triangle OSN, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha according to the sum rule that states that the sum of the angles in a triangle is equal to 180 degrees. It's very easy to see from the drawing that the upper right triangle PQO is similar to the lower right triangle ONS according to angle similarity rule. That is to say, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So if you found out that all the figures of the upper right triangle PQO are corresponding equal to all the figures of the lower right triangle OSN, and therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. If you found out that the right upper triangle PQO is similar, this is the sign of similar, to the right lower triangle ONS according to angle similarity rule. And from the fact that those two right angles are similar to each other, we derive that the following relationship exists between their sides. We derive that side SN of the right lower triangle SNO over side PQ of the right upper triangle PQO is equal to side OS of the right lower triangle ONS over side PO of the right upper triangle PQO. Repeat again. From the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side SN of the right lower triangle ONS over side PQ of the right upper triangle PQO is equal to side OS of the right lower triangle ONS over side PO of the right upper triangle PQO. SN is the missing side, so we leave it as it is. Over PQ. PQ is the line segment that we are looking for in this question, and it is equal to x. We have to find out the value of x. So PQ equals to x, and it is equal to OS. OS equals to 2 units in its length, according to what is given us the question, over PO. We already found out that PO is the radius of this circle, that is equals to 3 units in its length. So to that, we found out that Sn over x equals to 2/3. Here we will multiply this equation by x, and we get that the missing side Sn is equal to 2/3 x. This is the missing side Sn is equal to 2/3 x. Write it down. Sn equals to 2/3 x. In the next step, we'll define the size of this angle as beta, and we will focus on this right small green triangle, triangle SNM. This right small green triangle SNM, this angle equals to beta, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus beta. Why? Because 90 degrees minus beta plus beta is 90 degrees, and 90 degrees plus 90 degrees is equals to 180 degrees. That is the sum of the angles in any triangle. In the next step, we focus on the big right triangle, triangle PTM. On the big right triangle, triangle PTM, this angle equals to beta, and therefore angle beta is a common angle that belongs to both triangles. Angle beta belongs to the pentagon NSM, and angle beta belongs to the big right triangle, triangle PTM. So this angle equals to beta, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus beta, according to the same rule that states that the sum of the angles in any triangle is equal to 180 degrees. It is very easy to see from the drawing that the big right triangle PTM is similar to the small green right triangle NSM. I will explain anyway why those two right triangles are similar to each other. First of all, this is angle beta, that is a common angle that belongs to both triangles. So you can write down that angle beta equals to itself as a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees one squared and therefore they are equal to each other. So if you found out that all the figures of this big right triangle PTM are correspondingly equal to all the figures of this green right small triangle NSM. And therefore those two right triangles are similar to each other according to angle similarity rule. So right now, if you found out that the big right triangle PTM is similar to the small green right triangle NSM according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side SN of the small green triangle NSM over side PT of the big right triangle PTM is equal to side SM of the green small right triangle NSM over side PM of the big right triangle PTM. It is given as the question that line segment PT equals to line segment TS. So if we define the length of line segment PT as A, then the length of this line segment TS must be also equal to A because they are equal to each other. So from the fact that the right big triangle PTM is similar to the right green triangle NSM, we derive that side SN of the small right triangle ONS or side PQ of the big right triangle P, from the fact that the big right triangle PTM is similar to the small right triangle NSM, to the small green right triangle NSM, again, from the fact that the big right triangle PTM is similar to this green small right triangle NSM, we derive that side NS of the small right triangle MSN or side PT of the big right triangle PTM is equal to side SM of the small right triangle NSM over side PM of the big right triangle PTM. We already found out that NS equals to 2/3 x over PT. According to our definition, PT equals to A units in its length, and it is equal to SM. SM is the missing side, so we leave it as it is. Over PM. PM is the diameter of this semicircle. The radius is 3, therefore the diameter is 6. It's twice as long as the radius. So the diameter PM is 6. So in total, we should found out that 2/3 x over a equals to sm over 6. Here we will cross multiply this equation and we get that 2/3 x times 6 equals to ASM. This will be equation 1. According to equation 1, we found out that 2/3 x times 6 equals to ASM. 6 over 3 is 2, and 2 times 2x is 4x. So in total, this side of the equation, we have 4x. So according to equation 1, 4x equals to ASM. So again, we found out that according to equation 1, x equals to ASM. In the next step, I will repeat on rule 15 and we will implement rule 15 in our drawing. We already talked on rule 15 in the previous lectures. So according to rule 15, if chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. Again, if chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. So in the drawing we have a circle. This is chord AB that intersects with chord CD at point O. So in this drawing, according to rule 15, the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can actually implement rule 15 in our drawing. Why? Because in our drawing, we have chord TM that intersects with chord AB at point S. Again, chord TM intersects with chord AB at point S. So all the requirements of rule 15 are satisfied, and therefore we can implement rule 15 in our drawing. So at the moment we found out that in our original drawing, chord TM intersects with chord AB at point S. At point S. Therefore, we can implement rule 15 in our drawing. According to rule 15, the following equation will be true, that TS times SM equals to AS times SB. Again, according to rule 15, TS times SM equals to AS times SB. So, I'll write it down. TS times SM equals to AS times SB. Repeat again, according to rule 15, TS times SM equals to AS times SB. TS is A according to our definition times SM. SM is the missing side, so we leave it as it is. And it is equals to AS. What is the length of AS? AS in total equals to AO plus OS. So AS equals to AO, that is the radius of the circle, that is 3, plus OS, that is 2. So in total, AS equals to 3 plus 2, that is 5. So AS equals to 5 times SB. SB equals to 1 unit in its length according to what is given as the question. So So in total we found out that ASM equals to 5 times 1. 5 times 1 is 5. So in total we found out that this will be equation 2. According to equation 2, A times SM equals to 5. This is according to equation 2. Well, according to equation 1, we already found out that A times SM equals to 4x. So now according to equation 1, we should find out that A times SM equals to 4x. So we have two different equations for the expression ASM. Therefore, we get equation 3 that states that ASM according to equation 1 must be equal to ASM according to equation 2. And again, equation 3 states that ASM according to equation 1 must be equal to ASM according to equation 2. ASM according to equation 1 equals to 4x, and it must be equal to ASM according to equation 2. ASM according to equation 2 equals to 5. So in total, according to equation 3, we actually found out that 4x equals to 5. Here we will divide this equation by 4 and finally get that x equals to 5 quarters. 5 quarters is 1.25. Again, 5 quarters is 1.25. So if you found out that the length of this line segment PQ is equals to x is equals to either 5 quarters units in its length, or in terms of numbers, PQ is equals to x is equal to 1.25 units in its length. PQ is equals to x is equals to either 5 quarters units, or in terms of numbers it is equals to 1.25 units in its length. So we finished with the second question. In the next step, I'll start on the lecture. We'll start with the first question, of course. The first question on our test was to find out the area of this green shape. So in the drawing, we have a circle inside this big semicircle. We also know that this is line segment AQ, this is equals to 4 units in its length. This is line segment TB, this is equals to 1 unit in its length. This is angle AQP, this is the right angle. This is angle STB, it is also a right angle. Again, our task is to find out the area of this green shape. So first of all, we define the radius of the big semicircle as x and the radius of this small circle as y. In addition, we define the center of this small circle, this point is point O, and we define the center of this big semicircle. This point is point C. We define the point of tendency of tangent AB with this small circle. This point is point N. Likewise, we define the point of tendency of tangent PQ with this small circle. This point is point H. We define the point of tendency of tangent ST with this small circle. This point is point L. And finally, we define the touching point of the small circle with the big semicircle. This point is point K. In the next step, we join points O and N together by straight line. Point O is the center of the small circle. Point N is the point of the small circle itself. So therefore, ON is the radius of this small circle. Is equals to y according to our definition. The radius ON that is equals to y. The radius ON is drawn to point N, that is the point of tendency of tangent AB with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO according to rule 1. If AB is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. This is angle PQA, this is the right angle. AB is the diameter of the semicircle, therefore it is absolutely a straight line. So if we focus on the upper side of the straight line AB at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line AB at point Q? We have this angle that is the right angle, plus this missing angle. In total they must be equal to 180 degrees. Those two angles in total must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. Likewise, we know that this gives us the equation that this is angle STB, that is the right angle. So if we focus on the upper side of the straight line AB at point T, here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the upper side of the straight line AB at point T? We have this angle that is the right angle plus this missing angle. In total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. In the next step we join points O and S together by straight point O and L together by straight line. OL is of course the radius of the small circle that is y. The radius OL is equals to y. The radius OL is drawn to point L, that is the point of tendency of tangent ST with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent ST will be perpendicular to the radius LO. If ST is perpendicular to LO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So in quadrilateral OSTN, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total must be equal to 360 degrees according to the rule. The sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral OSTN, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be at its right angle if not a square. So we know to quadrilateral OSTN is right angle because it has 4 right angles. But we also know that the opposite sides of rectangle are equal to each other. So rectangle OSTN, side OS must be equal to the opposite side TN. But OS is y, therefore the opposite side TN must be also equal to y units in its length. Repeated on the same process on this side of the drawing. That is to say, we join points O and H together by straight line. OH is of course the radius of the small circle that is y. The radius OH that is equals to y. The radius OH is drawn to point H, that is the point of tendency of tangent PQ with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent PQ will be perpendicular to the radius HO. If PQ is perpendicular to HO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So in quadrilateral OHQN, we have 1, two free right angles. The sum of free right angles is 270 degrees, so 270 degrees plus the size of this four pieces again, in total it must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this four pieces again must be equal to 90 degrees in size. So inside quadrilateral AONQ we have four right angles, and according to rule 5, any quadrilateral that has four right angles must be a rectangle if not a square. So we have to quadrilateral AONQ is a rectangle because it has four right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle AONQ, side AO must be equal to the opposite side NQ. But AO is y, therefore the opposite side NQ must be also equal to y unit in its length. This is line 7 QT. Line 7 QT is part of the straight line AB. Again, line 7 QT is part of the straight line AB. And you know that part of a straight line must be also a straight line. So QT must be also a straight line. QT in total equal, therefore, because of the fact that QT is a straight line, it means that QT in total must be equal to QN plus NT. So QT in total equals to QN, that is Y, plus NT, that is Y. So QT equals to Y plus Y, that is 2Y. AB is the diameter of the semicircle. The radius of the semicircle is x, therefore the diameter equals to 2x. So AB equals to 2x from one side. Again, AB equals to 2x from one side, but from the other side, AB equals to AQ plus QT plus TB. Again, AB in total equals to AQ plus QT plus TB. But again, from the other side, AB in total equals to AQ plus QT plus TB. AQ is 4, QT is 2y, and TB is 1. And again, AQ is 4, QT is 2y, and TB is 1. So in total, 2x equals to 4 plus 1, that is 5 plus 2y. Again, 2x equals to 2y plus 5. Here, subtract 2y from the equation, if I found out that 2x plus 2y equals to 5. Here, we took 2x, a common factor from those two expressions, so inside the brackets we have x minus y. So in total, if we found out that 2 times x minus y equals to 5. Here we divided this equation by 2, and we found out that x minus y equals to 5 over 2. 5 over 2 is 2.5. So if we found out that in total that x minus y equals to 2.5. What is the length of this short line segment Cn? From the denominator it is very easy to see that Cn is in total equals to CB minus NT minus TB. Again, Cn in total equals to CB minus NT minus TB. Repeat again, Cn in total equals to CB minus NT minus TB. So Cn in total equals to CB. CB is the radius of the semicircle. That is equals to x minus NT. NT equals to 1, and TB equals to 1. Repeat again, CB equals to x, NT equals to y, and TB equals to 1. So in total we found out that TB equals to x minus y minus 1. X minus y is 2.5, so we substitute x minus y by 2.5. So in total Cn must be equal to 2.5 minus 1. 2.5 minus 1 is 1.5. So we found out that the length of the short line segment Cn is equal to 1.5 units in its length. Because of the fact that the small circle touches the big circle at point S, we have here internal notch between the small circle and the big. Again, because of the fact that the small circle touches the big semicircle at this point K, we have here an internal notch between the small circle and the big semicircle at point K. So we can implement here rule 9. Repeat quickly on rule 9. According to rule 9, if two circles touch each other internally, then the straight line that connects the circles together passes through their touching point. In the domain you have two circles, the center of the big circle is here at point O, the center of this small circle is here at point N. The straight line that connects the circles together is of course the straight line OM. And according to this rule 9, the straight line OM must pass through their touching point at this point P. Again, according to this rule 9, the straight line OM must pass through point P, that is their touching point. O and P is one straight line. Again, O and P is one straight line. according to this rule rule 9. So we can implement rule 9 in our drawing. Why? Because in our drawing we have an internal notch between the small circle and the big semicircle at point K. That is to say they touch each other internally at point K. The center of the big semicircle is here at point C. The center of this small circle is here at point O. The straight line that connects the centers together is of course the straight line CO. And according to rule 9, the straight line CO must pass through their touching point, that is point K. Again, according to rule 9, the straight line CO must pass through point K, that is their touching point, or COK is one straight line. Again, according to rule 9, COK is one straight line. If COK is one straight line, it means that CO must be equal to CK minus AK. Again, if COK is one straight line, it means that CO must be equal to CK minus OK. Again, CO equals to CK minus OK. So CO equals to CK, that is the radius of the semicircle, that is X, minus OK, that is the radius of the small circle, that is Y. So in total, CO equals to X minus Y. This line cement CO equals to X minus Y units in itself. But we already found out that X minus Y equals to 2.5. X minus Y equals to 2.5, therefore CO is equals to X minus Y equals to 2.5 units in itself. We already found out that CM equals to 1.5 units in itself, and ON is the radius of the small circle, that is equals to 1 unit in itself. In the next step, we implemented the Pythagoras theorem on this right triangle CON. According to the Pythagoras theorem, in any right triangle, the score of the hypotenuse equals to the sum of the scores of the perpendiculars. So I call it the right triangle CON, and we implemented on this right triangle CON the Pythagoras theorem. This is the right triangle CON that according to the original drawing, in this right triangle CON, OC squared, that is the score of the hypotenuse, equals to ON squared plus NC squared. OC is 2.5, therefore OC squared is 2.5 squared, that is 6.25, and it is equals to ON squared. ON is Y, therefore ON squared is Y squared, plus CN squared. CN is 1.5, therefore CN squared is 1.5 squared, that is 2.25. So in total, if you found out that 6.25 equals to Y squared plus 2.25. Here we subtracted 2.25 from this equation, and we found out that 6.25 minus 2.25 is 4. So 4 equals to Y squared. Here we took out of this equation, and we found out that Y equals to the square root of 4, that is 2. So the radius of the small circle Y equals to 2 units in its length. We have only found out that X minus Y equals to 2.5. But Y is 2, so X minus Y is X minus 2, that is equals to 2.5. Here we added 2 to this equation, and we found out that X equals to 2 plus 2.5, that is 4.5. 4.5 is 9 over 2. So we found out that the radius of the big semicircle, X equals to either 4.5 units in its length, or 9 over 2 units in its length. Our test is to find out the area of this green shape. The area of the green shape must be equal to the area of the big semicircle minus the area of the small circle. Again, the area of this green shape must be equal to the area of the big semicircle minus the area of the small circle. Repeat again, the area of the green shape must be equal to the area of the big semicircle minus the area of the small circle. The radius of the semicircle is x, therefore the area must be equal to pi x squared over 2. Minus the area of the circle, the radius of the circle is y, therefore the area of the circle must be equal to pi y squared. X is 9 over 2, therefore x squared is 9 over 2 squared. So in total this expression equals to pi over 2 times 9 over 2 squared. Y is 2, so y squared is 2 squared, that is 4, so in total this expression equals to 4 pi. We open the brackets here, and found out that 9 over 2 squared equals to 9 squared, that is 81, over 2 squared, that is 4. So in total this expression equals to 81 pi over 2 times 4. Minus the area of the circle, that is 4 pi. Here we multiplied 4 pi by 8, and then we multiplied minus 4 pi by 8, and then we divided by 8 in order to overcome factor of this expression. Minus 4 pi times 8 is minus 42 pi divided by 8. 81 pi over 30, 81 pi minus 42 pi is 49 pi over 8. So we have found out that the area of this green shape equals to either 49 pi over 8 square units in its size, or in terms of numbers, the area of this green shape equals to 19.32 square units in its size. So we finish with the first question. In the next step I presented to you the second question, and we answered on the second question of this lecture. Our task in the second question is to find out the length of this line 7PQ that equals to x. We have to find out the value of x. So in the drawing you have a semicircle. Point O is the center of this semicircle. This is line 7 OS, that is equals to 2 units in itself. This is line 7 SB, that is equals to 1 unit in itself. This is angle PQS, that is a right angle. This is angle PTS, that is also a right angle. Again, our task is to find out the length of this line 7 PQ that is equal to x. We have to find out the value of x. So first of all, we completed the semicircle to a circle, and we extended line 7TS by side line until it touches the circle. We define the touching point of the extended line 7TS with this circle. This point is point M. In the next step, we join points P and M together by side line. By doing all those constructions, we created peripheral angle PTM, that is a right angle. And according to Rule 5, any peripheral angle that is equal to 90 degrees in size must subtend on the diameter of the circle. Peripheral angle PTM, that is a right angle, subtend on the PM, and therefore PM must be the diameter of the circle according to Rule 5. Point O is the center of the circle, point B is the point of the circle itself, therefore OB is the radius of this circle. OB in total equals to OS plus SB. OS is 2, SB is 1, so in total OB equals to 2 plus 1, that is 3. The radius OP equals to 3, the radius OM also equals to 3. In the next step we did the construction, that is to say from point S, we drew perpendicular on the diameter PM. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point S and the diameter PM. This point is point M. By doing this construction, we created the right triangle OSN. Those two angles are vertex angles, and we know the vertex angles are equal to each other. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha, because they are equal to each other. So in this small right triangle ONS, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. It is the sum of the angles in a triangle. Likewise, in this upper right triangle PQO, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha, according to the symbol, that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we prove that the upper right triangle PQO is similar to the lower right triangle ONS, according to angle similarity rule. That is to say, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we prove that all the figures of the this upper right triangle PQO are corresponding equal to all the figures of this lower right triangle ONS, and therefore those two right triangles are similar to each other according to angle similarity rule. So if again we found out that the upper right triangle PQO is similar to the lower right triangle ONS according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side NS of the small right triangle ONS over side PQ of the upper right triangle PQO equals to side OS of the right triangle ONS over side PO of the upper right triangle PQO. And again, we derive that SN over PQ equals to OS over PO. SN is the missing side, so we leave this it is. PQ is X. That is the line segment that we are looking for in this question. OS is 2 and PO is 3. So in total, we found out that SN over X equals to 2/3. Here we multiply this equation by X and finally found out that SN equals to 2/3 X. In the next step, we define the size of this triangle as beta. We focus on the green right triangle SNM. The green right triangle SNM, this angle equals to beta, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus beta. Why? Because 90 degrees minus beta plus beta is 90 degrees, and 90 degrees plus 90 degrees it is equal to 180 degrees. That is the sum of the angles in a triangle. Likewise, in the big right triangle PTM, this angle equals to beta, therefore angle beta is the common angle that belongs to both triangles. This angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus beta, according to the symbol that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we prove that the big right triangle PTM is similar to the green right triangle NSM. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees minus beta, therefore they are equal to each other. And those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, this is angle beta, this is a common angle that belongs to both angles. So we can write down that angle beta equals to itself as a common angle that belongs to both angles. So if you prove that all the fingers of this big right triangle PTM are corresponding equal to the fingers of this small green triangle NSM, and therefore those two right triangles are similar to each other according to angle similar rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side SN of the green triangle SNM over side PT of the big right triangle PTM is equal to side SM of the green triangle SNM over side PM of the big right triangle PTM. And again, we derive that SN over PT equals to SM over PM. SN is 2/3 X. PT, according to our definition, PT is A, and it is equal to SM. SM is the missing side, so we leave it as it is. PM is the diameter of the circle, that is twice as long as the radius. The radius is 3, therefore the diameter must be equal to 6. So PM equals to 6. So in total, we should find out that 2/3 X over A equals to MS over 6. Here we cross multiply this equation and we found out that 2/3 X times 6 equals to A times SM. 6 over 3 is 2 and 2 times 2x is 4x. So in total this is the equation 1 we have 4x, so 4x equals to ASM. If it again according to equation 1, we should find out that 4x equals to ASM. So here we can implement rule 15 in our domain according to rule 15. If code AB intersects with code CD at point O, then the following equation is true that AO times OB equals to CO times OD. In the domain we have a circle and we have code AB that intersects with code CD at point O. So in this domain the following equation is true that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can implement rule 15 in our domain. Why? Because in our domain we have code TM that intersects with code AB at point S. Again, code TM intersects with code AB at point S. So all the requirements of rule 15 are satisfied and therefore we can implement here rule 15. Because again, in our domain, code TM intersects with code AB at point S. Therefore we can implement rule 15. According to rule 15, TS times SM equals to AS times SB. Again, TS times SM equals to AS times SB. And again, according to rule 15, TS times SM equals to AS times SB. TS is A times SM. SM is the missing side, so leave it as it is. And it is equal to AS. AS is 3 plus 2, that is 5. SB is 1. Yeah. AS is 5 and SB is 1. So in total ASM equals to 5 plus 1, that is 5 times 1, that is 5. So according to equation 2, ASM equals to 5, while according to equation 1, ASM equals to 4x. So we have two different equations for ASM. Therefore, we created equation 3 that says that ASM according to equation 1 must be equal to ASM according to equation 2. ASM according to equation 1 equals to 4x. Again, ASM according to equation 1 equals to 4x. And it must be equal to ASM according to equation 2. ASM according to equation 2 equals to 5. So in total, according to equation 3, we found out that 4x equals to 5. Here we divided this equation 3 by 4 and finally found out that x equals to 5 quarters. 5 quarters is 1.25. So she found out that PQ is equal to x. It is equal to either 5 quarters units in itself, or in terms of numbers, PQ that is equal to x is equal to 1.25 units in itself. I repeat again, the length of PQ that is equal to x, it is equal to either 5 quarters units in itself, or in terms of numbers, PQ that is equal to x is equal to 1.25 units in its length. Okay, thank you very much.